Hello, everybody. Welcome back. Hope you're doing well. In this video, we're going to be talking about reinforced concrete design once again. We're going to be covering the concept of flexural members, and we're going to be starting with a description of how to look at beams and how to understand flexural paths and some different variables that are involved in the design of flexural members. Um, as always, I like to start off with just an introduction to the concept, and I'm taking this concrete design course super slow because there's so many small details that need to get covered before you can really hop into problems. And I'm just going to start off today by talking about what flexural members are designed for, because in the last video we covered a concept of a simple span where you have a positive moment developing in your member, and that is creating a tensile face on the bottom that is bringing in these cracks. But since concrete is cast monolithically, or in other words, poured all at once, we need to consider that there are two different formations. We have simple configurations, and we can also have continuous or indeterminate. So once again, we already covered simple is a two support structure that develops a positive moment, and it's generally supports that are on each end. Now, continuous structures like the one I've drawn here have three or more supports and require more complex ways to analyze and develop these bending moment and shear moment diagrams. And the one takeaway that we need to take away from this figure is that now there are inflection points. So you see, we have this bend or bow on the bottom and then hogging at the top. And pretty much all that means is that you're transitioning from an area that has positive bending moment at the midspan and a negative bending moment at the supports. And that's typical for not just concrete members, but continuous members in general, where at the support you're going to be developing that negative moment. So, what does that mean for concrete design? In concrete design, we talked about previously that we need to place reinforcement in these tensile regions. So, for a continuous member, you're going to have a transition between bottom reinforcement, where the tensile force is being developed in the bottom strand because of that positive moment. And then you transition to a top reinforcement that is going to be acting at the negative moment region because you have inflection. The tensile face is now changing. And that's the main takeaway for continuous members. And that's the design philosophy for how reinforcement is placed fundamentally in the member. And you can see down here too, just a cross section of the different areas. You have reinforcement at the bottom for section AA. And then as you go to section BB, you're at that support. And now you have top reinforcement instead. And you can see the two different moments that are being applied. Now, in this video and in this problem specifically, we're just going to be covering the basics of what the variables are to design flexural members, and these are fundamental to understanding future design problems. So the first two variables that we already know that are typical for all beam problems in structural design are your H, which is the depth of your member, and the B, which is the width of your member. But now we're going to be talking about some new concepts, which is first the effective depth. And all effective depth means is that you are taking the distance between your top compressive fiber to the centroid of your reinforcement or your area of steel reinforcement. An area of steel reinforcement is represented by AS. And the reason that we have this effective depth is because we're going to be taking this as a design variable for future problems where we have tensile force being directed from the reinforcement and then a compressive force acting in the face of this compression block. But we're going to be talking about that in future videos, so don't you worry. All you need to know is that it is a design variable at the moment. And AS is another simple one. This is just the area of cross-sectional reinforcement that you have in your member, and it is represented by AS. And the way to calculate this is just to take the count of rebar that you have in your member and then multiply it by the area of the bar. So these bars range in different systems. You have different callouts for the type of rebar. And in this problem here, we have a 25M. And as you can see, I'm going to slide in a table over here. This is a way to call out what bar size you have. So for example, 25 m is simply representing that the diameter of your bar is 25 millimeters. And from that, you can take away what the area is, what the diameter of your bar is, and they're useful to find things such as the effective depth. Now, another important concept is going to be the reinforcement ratio, and this is another critical design variable. But for now, all you need to know is that this formula is going to allow us to determine how much reinforcement is in our member with respect to the size of our member. And the purpose of this variable is just to tell us if the designer has over reinforced, under reinforced, or designed the beam to be balanced in reinforcement. And that'll all be covered later. Another important concept is going to be concrete cover. And in the Canadian code, it's covered in this code here. So that's CSA A23.3. And all the code is telling you is that your concrete cover is going to be designed based on two things. That is going to be your exposure class and your exposure condition. So those two things, all that means is that for every concrete mix, it is designed for a specific environment. And the member in general is designed for a specific purpose. So it could be a footing, it could be a beam, it could be a slab. There's many different flexural reinforced members. And depending on where the environment is for that specific mix design, you need a certain cover between your reinforcement. Now, why is that? That's because your reinforcement is subject to damage by corrosion and by infiltration from harmful elements, things like chlorides and water. And the further that distance is from your reinforcement based on this concrete cover, the more protected it is from those infiltrants. And in addition, if there is a fire in your structure, this cover will slow the damage that will occur to this metal element, right? So those are the two reasons why we have concrete cover. And depending on where it is, specifically, for example, if you had a footing, you're going to have a much higher cover because that footing is exposed to the earth. And earth, obviously, can have a groundwater table, and water can seep into this member. So you want a larger cover to prevent that. So those are some basic design principles for why cover is chosen. And another important design requirement is going to be based on your minimum bar spacing. So you see in this picture over here, I have a reinforced beam or member that has two layers of reinforcement. And the reason why that is because reinforcement may be designed to a certain quantity and they will be touching each other if they're all in the same layer. And that's no good for concrete because concrete needs to get in between these tiny cracks that are between the reinforcement. And in order to do that, it needs space. And if you can't squeeze them all into one layer, then you're going to add another layer. You're simply going to move up a level in order to place that additional reinforcement. Now, in order to design this minimum bar spacing, we have to look at A23.3. We go to the code and we find that the minimum spacing will be based on the maximum of these three design parameters. So we have 1.4 times the diameter of your bar, 1.4 times the max aggregate size in your mix, or 30 mil. So depending on which is the max, that will be your minimum required spacing between bars. So now we can hop into the problem and see how to solve for each of these different parameters. So we have a simply supported reinforced concrete beam, and it has the following cross-section. And the beam is reinforced with 625 m bars and two layers with a concrete cover of 50 mil. Concrete mix has a max course aggregate size of 20 mil, and it wants us to determine the effective depth, the area of steel reinforcement, and the reinforcement ratio. Now, in order to get a better idea of what we're looking for, let's take a closer look at this area of reinforcement. Alrighty, so now that we have a closer look of our reinforced area, we can now determine what we're looking for. So effective depth is going to be once again at the centroid of this reinforced area. So this red X is representing the point that we're trying to solve for with respect to the top compressive fiber. And in order to get to this point, we have to subtract from the total depth of our section. So we're taking 600 and we're subtracting the cover between these rebar, the diameter of each bar, and half of this minimum spacing between the two layers. So let's see what that looks like right here. We have the D is going to equal to the H minus the cover minus the diameter of the bar minus S min over 2. Now S min needs to be solved for first. So we have that S min will equal to the maximum of these three different variables that we have on the right side. So we have 1.4 times the diameter of the bar, and a 25M is 25 mil. 1.4 times the max aggregate size, we know that's 20 given in the problem, and we have 30 as the base. And this, when solved, will give you 35, give you 28, and obviously 30. So the 35 is your max, so your S min will equal to 35. So we can assume that as the spacing between these two layers of rebar. Now solving for that, we can start plugging into our problem. We have H, which is 600, subtracting the cover, which is given as 50, subtracting the diameter of our bar, which is 25, and subtracting S min, which is 35, and then dividing by 2 since we're taking the centroid of that area. And solving for that, you will be left with a value of 507.5 millimeters. And that's your first answer. The second one is asking us for the area of steel. So AS is going to equal to the number of bars times the area of each bar. We know that we have 6 based on the count. And then for the area of a 25M bar, if you refer to that table I showed you earlier, each bar is going to be 500 mil squared. So that means this value is going to be 3,000 millimeters squared. Lastly, we have the reinforcement ratio, which is just plugging in all of these values that we already solved for. So we have AS, which is 3,000 on top. That's in millimeters squared. And on the bottom, we have 400 for the base width and 507.5. Those multiplied together give you millimeters squared. And then solving for that, you have 0.0148. And that's unitless, but can also be thought of as a percentage. We'll talk more about this number in future videos. And that's all for this problem. Next one, we're going to be talking a little bit more about the flexural design and how to analyze a cross-section and design for a quantity of reinforcement. Thanks for watching.